So let me sort of continue the topic that I was talking about last time. So unfortunately, I don't think I'll have enough time to talk about surface topological order, except maybe one slide at the very end. But let me tell you about some of our very recent work where we think we have made some progress in understanding what's going on in this magic angle graphene. It's really going to be based on this particular paper where we analyze the effect of interactions sort of in the pristine system, which doesn't, has no strain and no disorder and so on and so forth. We think we have some consistent story for the ground state, at least at certain filling fractions where an insulating, where an insulator is seen. Okay, so this ground state you're going to see is at least the one, the proposed ground state is conventional in many ways. It's you can think of it as a slated determinant or a Hartree Fock state. But the kind of order that appears is, at least to me, was extremely unexpected. And there are some interesting topological aspects of that state. So although the state itself maybe has ultimately a simple description in terms of a lambda order parameter, some of its topological aspects are extremely interesting and may be related to the superconductivity that's seen in these systems. Okay, so that's the I'm going to focus on this particular preprint. So let me, before I actually start talking about more detailed issues, let me tell you one sort of big picture issue that we have been struggling with since the beginning of this field, and that is really how to think about magic angle graphene. Which of the two paradigms that we're used to in solid state physics is more appropriate to start thinking about the interaction effects. Okay, so as you all know, in magic angle graphene, you tune to this particular angle that was predicted by theorists actually, where the kinetic energy is small, interactions dominate. And we know two other examples like that in the past where you are in that regime, and they have very different approaches. Okay, so one is, of course, the quantum Hall effect. Strong magnetic field quenches the kinetic energy. Let's say you partially fill one of these lambda levels, and then you ask what happens. Okay, and we know the approach here is you use these wonderful analytic wave functions, and you can make progress like Laughlin did, try to write down correlated electronic state. There's also the physics of quantum Hall ferromagnetism. Although you are at an integer filling, you spontaneously break spin rotation symmetry by forming a ferromagnet. All of that is discussed using these sort of wave function approach. The complementary picture is solids like the cuprates. Okay, so again, the kinetic energy and there's a competition, U and T. But here you have a completely different approach. You take the band that has strong interactions, start in momentum space. This is kind of reminiscent of wave functions like this. But then you Fourier transform and go to real space, write down these Vanier functions. And then you have an advantage because the interactions are all local in real space. Okay, so you can sort of figure out what's going on, go to the Mott limit. And the question is, which of these two, write down a Hubbard model like we heard in the last talk, try to analyze that. Which of these two limits should we really apply to magic angle graphene? And that's really what we've been struggling with. And in some sense, you'll see that it's a hybrid between these two. So unlike lambda levels, where there's simply no way to write down a useful Vanier function description, you can write down a Vanier function description for graphene, for this magic angle graphene, but it involves extra bands. You cannot write it down for the minimal set of bands because there is some sort of topology. Topology here is not as strong as the Chern number of the lambda levels, but there is some topology which is related to the fact that these two Dirac points in this magic angle graphene have the same chirality. They descend from the same, the same node, the same valley of the two layers of graphene. And like we talked last time, you can sort of think of it as a combination of two lambda levels, okay, but with opposing magnetic fields in a single valley. Okay, so there is some aspect of the topology like this lambda level physics, but it's not so, the obstruction is not so strong that you can simply not write down a Hubbard model. You can write down some extended Hubbard model, but at least the model of the story today will be it pays actually to think in terms of this picture, the lambda level picture. In fact, at least our analysis is very reminiscent of the quantum Hall ferromagnetism in lambda levels, except there is some non-trivial physics coming from the fact that you have both kinds of lambda levels, and that gives it some richness, and the eventual answer is somewhat hard to guess. At least I could not guess it before these calculations were done. Okay, so just to remind you, this is kind of the setting of the band structure. There are these nearly flat bands separated by a gap to the other, to these remote bands. And one useful picture is to simply focus on these bands, project all your interactions into that, and try to figure out what the ground state is at various fillings. It turns out people have worried about these remote bands, so eventually we actually included some of them just to make sure our answers don't change. Okay, so this is a recap of the experiments and what we are going to be interested in. So you see, this is scanning, the filling of this nearly flat band. This is charge neutrality that corresponds to this electron density over here. And they see, at least in these experiments, an insulating phase at charge neutrality. So the main question we'll ask today is, what is the nature of this insulating state? Okay, so if it's a broken symmetry state, identify the broken symmetry. And later we would like to ask, can we extend this analysis to the other insulators? In fact, the insulator at -2 over here was the first one discovered in Pablo's group. Can a similar order occur there, and so on? So those are more complicated questions. You'll see that the physics at charge neutrality is already extremely rich. For the purpose of this talk, let me just focus there. Yes, in the absence of interactions, symmetry guarantees that these bands must touch. You cannot detach them, so it's really some interaction effect that if you see an insulator over here, it's really due to some electron-electron interaction. And then the insulator you get, I don't know if you can see the contrast. This is more or less realistic kind of parameters for this Moiré pattern. You get some insulator where there are 4 electrons sitting in each of these shadows, right? That's the Moiré pattern. That's kind of the insulating state that you are ultimately after. Okay, so just to give you a picture of the strategy, so it's going to get a little complicated, of course, as we go along, but just keep the strategy in mind. So here's where the realistic problem is. It has various parameters. So there's a band dispersion. We said there's this flat band, but actually it's not completely flat. There is some dispersion, at least in the realistic model. We have to live with that finite dispersion. There's also this parameter that takes you away from the ideal chiral model. Okay, so if this W0 hopping were absent, we would get this very idealized chiral model where the hopping is only between the A and B sublattices. In reality, this ratio is not 0, it's something finite, it's something like 0.7, and we have to live with this. So we have to deal with both of this if you want to get to the realistic system. Okay, but there is this idealized model where you scale away the band dispersion, kind of like what you do in the quantum Hall effect. You forget about the dispersion of the lambda levels, there is none. Let's throw away the dispersion, let's throw away this breaking of this chiral symmetry, and first discuss this point over here. And you'll see that in fact you can solve this exactly in some sense, and then you can try to put back the perturbations over here, or put back these effects. They may not be perturbations, put back these effects and try to get back to the realistic problem, and see if you can continue, you can still have control over this and make a sensible picture. Okay, so let's start first with this higher symmetry, the ideal point. Okay, so this is the realistic band structure. It's got some finite ratio of these 2 parameters. This is what the original band structure did, the Bistreisen-McDonald model. But we're going to go to this ideal limit where you have perfectly flat bands, very big gaps to all the other bands. And these wave functions, we said last time we had an analytic form for them in terms of these theta functions and so on. Okay, so the big simplification in this chiral limit is that I can take apart this 2 flat bands in many different ways. They're degenerate. But one of the ways in which I can take them apart is to look at their sublattice polarization. Okay, so it turns out in this limit, if I look at a particular valley and I look at a fixed sublattice, let's say valley K and sublattice A, that band always has Chern number 1. It's literally like the Landau level of graphene. You put on a magnetic field on graphene. In one of the valleys, the wave function lands entirely on one sublattice. The opposite sublattice in the same valley has the opposite Chern number. Okay, so this was a statement that it looks like a pair of opposing Landau levels in each valley that live on opposite sublattices. Okay, so if I fix a valley, the A and B sublattice index essentially labels the Chern number of the bands. Okay, so we'll see, of course, once you introduce dispersion, this is the flat band limit, you're going to get hopping between these two. You're going to get particles that hop between sublattices in the same valley. You'll get a mixing of the plus and minus Chern number bands, and that is actually the basis of the band basis. Okay, but in the flat limit, I can use this basis, which is more convenient. Okay, so this is essentially the problem that we have with the spin. So in each valley, you have these two bands, and you also have 2 spins. Okay, so ultimately, you get 4 per valley, so 8 bands in all, if you like, and you're asked to fill 4 of them. Okay, so I've arranged these bands in a slightly different way according to their Chern number. So you get both the K and the K prime valleys, and both the A and the B sublattices that change according to the valley to keep the same Chern number. And then, of course, you have up and down spins. Yeah. Yeah, that's this one over here. So I don't know if you were here last time. Because of lattice relaxation, you move away from the simple-minded picture and it gets some reduction. And we're going to switch it off all the way for a theoretical device. Okay, so it turns out the big simplification in this limit, which I'll show you in a few seconds, is that you get a very big symmetry. You're allowed to rotate all of these 4 states into one another. There's a U4 symmetry for this Chern number and a U4 symmetry for this one. And under those rotations, the Hamiltonian remains invariant. The purely interacting Hamiltonian remains invariant. So there's a huge symmetry over here that appears when you make these assumptions that you're in the chiral model and you're in the flat band limit. And we'll see that that big symmetry allows us to kind of solve this problem. And then we'll be interested in how this symmetry breaks down as you go towards reality. Okay? So this, if people have thought about quantum Hall physics, quantum Hall ferromagnets will recognize this as very, something that keeps appearing there. When you have quantum Hall effect in graphene with different valleys, spins, and so on, you're asked to fill a subset of Landau levels. Okay, so here they're not quite Landau levels; they're these nearly flat bands of graphene. But you're asked to fill 4 out of these 8 bands. And the question is, what are the different ways you can do that, and how do you parameterize this, the degenerate manifolds that you get? Okay, so let me talk a bit more about this generalized ferromagnet. Okay, the first thing is I want to simplify this problem. These 8 bands are a bit too much to, at least for pedagogical purposes. So let me just throw out the spin. Okay, so you can think of this as being spin polarized, if you like. We'll come back later and add the spin if we don't run out of time. We have spinless fermions. So instead of 8, we have 4 levels in all. You have to fill 2 of them if you want to find an insulator at charge neutrality. Okay, so you can consider many different states that you can write down depending on which of these 2, which pairs of states you pick. And a good way to parameterize that is, sorry, there's a typo, this is C dagger C. You write down a matrix Q an operator Q that takes on the eigenvalue +1 for all the filled energy levels and -1 for the empty energy levels. Okay, so it's not quite a projector. It's this. You can also write it as the commutator over here. It just tells you which ones you picked and which ones are left empty. Okay, so you can think of some. So I'm going to discuss everything in terms of this Q. So let me just give you some intuition. For example, you're given these 4 states. and you decide to just fill the states that live on the sublattice A. Okay, so the Ka and the K prime A states, let's say you decide to fill those, that is given by the Q matrix sigma Z. Okay, so sigma is going to be the sublattice matrix, sigma Z plus minus 1 is the A and B sublattice. Okay, so if you just fill the A sublattice, that is simply the matrix sigma Z. In fact, this is the state that is induced if you have a proximate so-called HBN substrate, okay, that breaks the symmetry between the A and B sublattices. All the electrons fall into one sublattice. It's sometimes called the Valley Hall state, and you can see why. In one valley, you have one Chern number, in the opposite valley, you have the opposite Chern number. Another simple state you can write down, put all the electrons into a single valley, okay, regardless of which sublattice you're on. Put them all, let's say, in the K valley, both the A and B sublattices. Okay, that's another state that you can easily write down in this, in terms of this Q, and that's just the valley Pauli matrix tau Z, which labels the plus and minus values. Okay, so here's a bunch of different states. We just went through these. You can also decide to fill both of these levels. That's the quantum Hall state. Okay, there's two Chern 1 bands that are filled. That's the sigma Z tau Z. But then you have some more interesting states where you actually develop a coherence between the opposite values. Okay, so we'll call those inter-valley coherent states. So let me actually go through that taxonomy, if you like. States where the valley quantum number is spontaneously broken. Okay, so what do these states correspond to? So we know, of course, the two valleys have different crystal momentum on the graphene, on the carbon atom scale. If you get a spontaneous coherence that scatters you between the two valleys, it's essentially a charge density wave, or some density wave, which is of the scale of the carbon atoms. So in this blown up image, it's some density wave that triples the unit cell at the level of the carbon atoms. A much smaller scale than, of course, the Morey scale. Okay, so this almost looks like an internal symmetry if you're sitting at the big scales of the Morey lattice. It's like you have this U1 valley symmetry. A number of electrons in each valley is conserved, but then that spontaneously breaks because of this coherence, and you end up breaking this microscopic translation symmetry. The important thing is that there are many different ways in which you can break this threefold symmetry, this translation symmetry. Okay, there's a charge density wave which has this form, just scattering between the valleys, but you can also have these two where you essentially modulate the hopping in a way that has some finite period. Okay, so this sigma x times these taus, tau x and tau y tells you scatter between the valleys, and the sigma x tells you that you do that by changing the strength of hopping on the carbon atom sides spontaneously. It's like the Kekulé pattern, yeah. Yeah, so you'll see that the gaps we find are not that different from the interaction scale. So I'm really talking about the zero temperature physics with the gap. The actual thermodynamics, what happens when you heat it up, is a little more complicated. Yeah. Yeah, so this is really the zero temperature, what is happening at the ground state of the system. Yeah, so this one involves modulating the magnitude of the hopping, and this actually is an interesting one where you modulate the phase of the hopping. Okay, so you have sigma y, the imaginary Pauli matrix in the usual notation. It's like you spontaneously change the phase of hopping, and this is it's also an IVC, but it breaks time reversal symmetry because you're going to set up some circulating currents. But they're all IVC kind of order parameters. I'm going to use this inter-valley coherence order to IVC that notation. They're all IVCs, but they have different form factors, and that's going to be important for which one is actually going to be selected. Okay, so these are the kind of orders that you can get, and the question is, what do the interactions select, at least in this highly symmetric limit. Okay, so this is what our model Hamiltonian looks like. It's purely interactions. We have thrown away the kinetic energy at this point. There's a screen Coulomb interaction that couples to the densities. So there's density minus the background density. And what we want to do is we want to take the density of electrons and project them into these bands. Okay, so this is a projected density operator. very much like how you project the density into the Landau levels for the Landau level physics. Okay, so when you do that, you want to restrict your attention to the electrons that live inside this low energy subspace. So these electrons C, they of course have a Valley index, the spin and Valley. But in addition, they have two bands. There's a plus and minus band. So we're thinking of this as a two-component electron if you focus on one Valley. Okay. And then you have this matrix lambda that is really the wave functions of these electrons. When you go back and write down the density operator, you've got to evaluate these matrix elements between the wave functions of these states and the density in Fourier space, which is e to the iq dot r. Okay, so these form factors are completely crucial, and they encode all the topology of these bands. The geometry of these bands is all sitting in these form factors. Okay, so if you were to get rid of them, if you forget about this lambda, if you simply write your density as some simple quadratic form of the band operators, the answers you get will be completely different. And it's really here that this problem differs, let's say, from the problem of cuprates. In cuprates, you have this band with essentially trivial form factors, okay, because there's a simple Wannier representation, and there's nothing interesting in this type of structure. Okay, so here, not only do you have two bands, that's important as well. This form factor is non-trivial and keeps track of how these wave functions change as you move around the Brillouin zone. Okay, so now the big simplification we get in our chiral model limit is that this form factor is extremely simple, okay, and it just takes this form. I won't tell you the details of what these functions look like, but the only matrix it depends on is the product of the sublattice and the Valley matrix. And this is really a consequence of if you pick a particular Valley and you pick one of these bands, the plus or minus band in this chiral model, the electrons are completely on one or the other sublattice. Okay, so then these overlaps, there's no overlap between sublattice A and sublattice B, of course, in this overlap matrix. That's why you end up getting something that's diagonal in the sublattice and Valley space. Okay, so this is what allows you to solve this limit exactly in some sense, because there is, yeah, good question. So so the geometry of this device is you have these bilayer sheets, and then you have some insulating substrate, and then you have some gates. So if it was not for the gates, you would have the Coulomb interaction, 1/r Coulomb interaction, but eventually it's screened by the gate. So it's really a question of how far is the gate, and that varies depending on your sample. So the parameter we used, I think, was kind of for the first batch of samples where about 40 nanometers. It's about 2 or 3 times the separation between these Moiré unit cells. But we varied that. It's something you should vary and check. But yeah, it's you could go from the limit where the screening is within the unit cell of the Moiré lattice to something that is beyond 2 or 3 unit cells. Yeah, right. There's a dielectric constant of about 10 with the, yeah, that's right. Yeah. You have to be a little bit careful how you include this dielectric constant, because it also, you're actually talking about the physics of these isolated bands. It's also the electrons of graphene that are, all the other bands that are screening. You want to use some RPA dielectric constant for all of those bands, cut it off, and then put in the dynamics of the lowest energy bands in your model. So it's, yeah, we had a range. Again, I'll show you there's a range of dielectric constants we use. And no, they depend on momentum. I just suppressed all of that, because the thing we'll use is this form, not the precise thing. Yeah, we have the expressions for the, at least pictures of what they look like. Not yet. It will be, but not yet. Yeah. Okay, so so we want to find the ground state of this Hamiltonian, and it turns out there's a class of ground states you can find exact exact ground states which satisfy this condition, this Q matrix. So we're going to write down ground states that are slated determinants, very simple kind of states, and they are parameterized by this Q matrix that tells you which states to occupy, which states to empty, and this the condition is that this Q should commute with this form factor lambda. In other words, it commutes with this matrix, the product of sigma z and tau z. So Qs that commute with that, which also have the trace zero condition, tells you there are as many empty as filled bands. Those states we claim are ground states of this Hamiltonian. And the way to show that, it's kind of simple. It's very similar to how people show that in the quantum Hall ferromagnets, the ferromagnetic state is a ground state of the interaction Hamiltonian. Okay, so you know that this interaction strength, this screen Coulomb, all of these coefficients are non-negative. So this is a positive definite operator. So it's sufficient, if you want to find a ground state, it's sufficient to find a zero energy state. Okay, so that is a ground, that's guaranteed to be a ground state. What you're not guaranteed, of course, is that's the only ground state. Okay, so that's something we can't prove, but we can show this is a ground state. So the claim is, let's say I take a state that looks like this. I'll construct at least one ground state very easily. Take a state that looks like this, where I completely fill, this was the Valley Hall state. Okay, so, this is the Valley Hall state where we fill electrons in this particular band in one valley, and in this band in the other valley. Okay, so they have a net Chern number 0. And now I imagine acting on the state with the density operator. Okay, so what we'll show is that the density operator annihilates this particular state, and because it annihilates the state, it's a zero energy state. And you can kind of see that because if you have a finite Q, what does a finite Q do? This form factor is such that you do not mix, you do not go between these different levels. That's kind of the key thing. The form factor is diagonal in sigma z tau z. So when you kick an electron over here to give it a momentum Q, you have to live within this particular band. And when you do that, of course, you find it's a filled band, right? So you find that there's some other electron there, and Pauli exclusion will kill the state. Okay, so this basically proves that for this limit of simple form factor, state like this, and all these other states, all these other slater determinant states are zero energy states, which are essentially ground states of this Hamiltonian. We don't know if they are the unique ground states, but we know certainly that they are in the ground state manifold. Okay, so in that way, you're able to solve this problem, no dispersion chiral model. And the next task is to take this big set of ground states, big space of big manifold of ground states, and figure out which of them, how they get split. And see if there's a consistent solution for one that gets split and gets isolated. Okay, so let me just quickly tell you some of these ground states of this high symmetry point. So the two we talked about before, Valley polarized and Valley Hall, are obviously ground states. But now let's talk about the inter-valley coherent states. We talked about 3 of them before. So it's not like this condition allows any old state. It has some restrictions. For example, it kicks out the CDW state. And you may, maybe for good reason, CDW is going to be bad energetically. It has pileup of charge in some regions and on others. You forget about the state. But these 2 are still ground states of this extended model. CDWs, or if you like, bond density wave and this funny current density wave are both allowed ground states within this large generalized ferromagnet manifold. Okay, simply because these order parameters you can check commute with this lambda, the sigma z tau z. Okay, so we have a bunch of different states, and now what we'd like to do is we have kind of solved this problem over here, we think, and we'd like to introduce these non-ideal things. Let's start by introducing the band dispersion. Okay, so I'll remain in this chiral model, but I'll introduce the band dispersion and see how things get split. Yeah, so let's just go back. Let's pick one of these. So this is a simple example. So what happens once you can think of it in a mean field picture if you like. Let's say you have this ground state, and now you look at the excitations above that ground state. What happens essentially is that these levels over here, they get exchange split. Think of it like a ferromagnet. You filled all the down spins, and the up spins levels are empty, and they have an exchange gap. Yes, that's the only scale in this problem, yeah. It will be determined by the interaction strength, roughly set by the interaction strength. So the interactions are like tens of milli-electron volts, and that would be the gap scale. So I'll show you later, we do more careful Hartree-Fock calculations and actually get a scale for the gap. Okay, so let's put in this band dispersion. So now what happens is that you allow for certain fluctuations. Okay, so electrons that started out in one of these particular states can now tunnel into the opposite, same value but opposite sublattice. Okay, that's the dispersion. And if you now ask what is the, how do the states split, you can easily argue that the states that get pushed down in energy are the ones that can do this fluctuation. Okay, so if you have electrons that fill up this band but leave this one empty, you can make this virtual process where you tunnel there and tunnel back. And it's like sort of like a super exchange interaction. You'll gain something of order t squared over u. Okay, so those states will be lower in energy, but if you were to fill both of these states, you're kind of Pauli blocked, and you can't take advantage of that, of that fluctuation. You can summarize that algebraically by asking that this order parameter, this q, anti-commutes with the kinetic energy. Yeah, that's kind of the condition. Kinetic energy is essentially the hopping between opposite sublattices. Okay, so you have these two conditions to satisfy, and that gives you the set of low energy states, and that's a subset of what you had before. It's still somewhat large. You have a U2 symmetry, and this symmetry is enlarged from whatever physical symmetry you had in this problem. You don't have spin, so you don't expect to get an SU2 except for some fine-tuning reasons. And the states that get picked out, one of them is where you completely fill up these states. Then, of course, these are empty. That's the quantum Hall state. You also you have this valley Hall where you fill that and fill that. So they're able to do this resonance. And then finally, you have one of these intervalley coherent state, the one that broke time reversal. I'll explain this notation K, the Kramer's, why it's called Kramer's in a little bit. But this is really the one that breaks time reversal, the one that has spontaneous currents in the ground state. Okay, so you find that all three of them are lowered in energy. And in fact, this pair over here, this set of three states, IVC should be thought of as two order parameters. This is the third one. This set of three rotates into itself under this U2 symmetry. So it's a degenerate manifold of states. That's what's picked by this dispersion. Okay, so that's one perturbation we have taken care of. Yeah, so the splitting is of order. This is the kind of energy scale for the splitting is small, but it's because these small splittings are important when you're trying to find the ground state. Okay, so we did one of them. We went up and put in the dispersion. Strictly, we should on top of this add the other perturbation, but let me do it right here. Let me individually add the other perturbation, which is to go away from this chiral model. If we end up finding a completely different set of states stabilized over here, that's going to be a problem, because now it becomes a question of detailed energetics. You have two perturbations, this one, that one. They do different things. Then it's a question of which one wins. Okay, so the very nice thing is it turns out that this will also stabilize some of the states we saw before. So there's kind of a clear winner. There's a clear winner that is stabilized both by this perturbation and that, so we can, with some confidence, figure out what's going on over there. Okay, so this perturbation I won't talk about in too much detail. You can look in the paper, but essentially the new condition you require for low energy states when you go away from this chiral model is that you have to commute with this particular matrix. Okay, so that matrix keeps track. So now the electrons don't sit only on one sublattice, they kind of leak into the other sublattice, and so that to make sure you don't lose exchange energy, you pick states that have this commutation property. Okay, so again, you can write down a list of states that satisfy this. So one of them turns out to be yeah, this is actually, so this should be valley polarized. That's the right matrix. So tau z commutes, of course, but it should be called valley polarized. Everything jumps into one valley. And the other state you find was actually one of the IVC states that you had before. Okay, so if you look at both of these perturbations, there's one set of states that is favored by both of them. And this is going to be the winner when you include both sets of perturbations. Okay, so this weird intervalley coherence with the circulating currents apparently seems to be the one that is picked out if you have both of these perturbations, at least individually, and you can make a case that you add them together, you would end up getting that particular state to be stabilized. Okay, so that's kind of the analytic argument, but let's see how well it does when you do some slightly more realistic numerics. So that was this Hartree Fock numerics that was done, which included multiple bands, not just the bands of very low energies, but also including things that are a little bit outside, and taking into account, making sure you don't double count, screening effects and so on. And this is what you see, that the ground state that you find, regardless of how many bands you keep, for a set of parameters which we think is realistic, the clear winner is this IVC state, this so-called K-IVC state. And then you have the first excited one, which turns out to be the valley polarized state, and then you have these other two, the valley Hall and quantum Hall are right on top of each other. And finally, you have the state which does not open a gap. It's semi-metallic, which has these Dirac points. Okay, so that's kind of the sequence. And you can also look at what happens to the band dispersion. This is the band dispersion before you added interactions. Once you add the interactions and go into this IVC state, like this question that was asked, forget about this gray line now, just look at the blue. You get an energy gap, and this gap you can see is about 40 millielectron volts. So that's the predicted gap, at least within the simple Hartree Fock numerics. Okay, so actually you can do more than that. Just to make sure as a sanity check, we wanted to make sure that we have more than just the ground state. We also have an understanding of what the low energy other states are, depending on where you are in parameter space. Okay, so you can do this experiment of, this is the realistic value of W0. You can imagine turning it down, dialing it down so you go closer to this chiral limit, and ask if the states you had there were the ones that show up at low energies. And in fact, that's exactly what happens. We had these four states, this K-IVC and these other two states, the quantum Hall and the valley Hall states, and they all are the ones at low energies. But if you go to the more realistic values of W0, this set goes up in energy, and it's really the valley polarized state, this purple one, that comes down. And this was done with different dielectric constants and so on. So you can actually verify in more detail what is the manifold of low energy states, and that exactly follows this intuition of which of these perturbations is coming in and breaking this large symmetry of this ideal model. This was done with spin, yeah. So the spin structure is kind of interesting. It's maybe a bit too interesting, so I won't get into it right now. It's extremely rich and so on. Yeah, so one of the things you can ask now just is, let's say you have this ground state, this IVC, this K-IVC ground state, and now imagine that you align the substrate, which gives you a splitting between the two sublattices. And as that splitting is increased, you expect to kill that intervalley coherent state and go into the so-called valley Hall state. There's an explicit field that's preferring that. And you can see that in the numerics that the order parameter for this IVC, which is like the equator of the sphere, the order parameter of this IVC begins to tilt as you expose it to the substrate field. And then eventually at some point it entirely goes along the North Pole, which is the direction in which the spin wants to sit. As soon as that happens, you lose this IVC order parameter. IVC order parameter is essentially an XY spin or a spin in the XY plane. And once you lose those in-plane components, you lose the order. That's this. This has a nice square root form which you expect for a mean field transition. One of the interesting things is the gap to the electrons remains intact across this transition. Barely changes, because it turns out the gap is the sum of the squares of these vectors over here. Okay, so you add in quadrature, so the gap remains open, but it's like a bosonic transition. There's a condensate that gets removed while the electrons stay gapped. If you think of this U1 order parameter like kind of like a superfluid, it's kind of a superfluid in terms of the intervalley coherence. This is a superfluid insulator transition. And you expect to see this. It turns out if you put in realistic values of the substrate potential, that's something like 30, where people actually see this valley polarized states experimentally. So you're pretty sure this is kind of consistent that this goes away before that happens. Okay, so it's all kind of, it's sort of consistent with what we know now. Okay, so now that we have this particular state, let's examine its properties. So it has a couple of very interesting properties that I want to highlight. So on the face of it, this seems to break time reversal symmetry. And the reason is if you just, essentially this Pauli matrix over here, the order that you have is one where you spontaneously develop a complex hopping amplitude. The usual hopping amplitude for electrons and between the carbon atoms of graphene is real. This state spontaneously gives you a small imaginary component. Okay, so it breaks time reversal, but it turns out that there's a modified version of time reversal that survives. A little bit like in an antiferromagnet, you can do time reversal and translate. Over here, what you can do is you can do the regular time reversal and then translate the valley phase by pi. Okay, so do this particular transformation, rotate the valley phase by pi. That gives you a new definition of time reversal. It's a combination of the old symmetries. And it turns out under this new definition, this order parameter is time reversal symmetry, T prime. There's some sort of antiferromagnetic time reversal present. Then the thing that's very interesting about this combination is that you can square it. And what you find is that it squares to -1. A simple exercise, tau y times the complex conjugation squares to -1. Okay, so this is really like a Kramer's time reversal symmetry. You're used to getting Kramer's in the context of spin. You have spin and you have spin orbit coupling. Time reversal squares to -1. That's the Kramer's time reversal. Here we have thrown away the spin. Forget about spin. Maybe it's all spin polarized. But the valley gives you another degree of freedom, kind of like a spin degree of freedom. In the usual setting, when you have other kinds of orders or the valley is preserved, time reversal is the ordinary complex conjugation time reversal. Okay, but in this particular state, the only kind of time reversal that remains is this Kramer's kind of time reversal. Okay, so you have conserved charge, you have Kramer's time reversal symmetry, you're in 2 dimensions. So the very natural question you can ask is, what is the Z2 topology of this state? Okay, this is kind of the context in which people talked about, Kane and Melly talked about the topological insulators, the Z2 topology. And in fact, it's very easy to argue that, in fact, it has a non-trivial Z2 topology. It's like the topological insulator, and it's kind of a one-line argument. Essentially in the state, what you do is you fill this, you make an intervalley coherent state. So you combine the electron in this level and that level. They are between the different valleys, different sublattices. You combine them together to get, you split them in that, along that axis. You fill that, and you do the same for this opposite Chern number band. Do the intervalley coherent state and fill that. Essentially, you've filled a Chern number 1 and a Chern number -1 level, and the two are related by this Kramer's time reversal symmetry. Okay, that's exactly the setting for quantum spin Hall or this 2-dimensional topological insulator. Okay, so the state that you found is an insulator. It has some kind of time reversal symmetry, some composite time reversal symmetry, and it's a 2-dimensional topological insulator under those symmetries. Okay, so yeah. That's right, yes. Yeah, yeah. Right, yeah. So you want to be, you need a, I think I have it in the next. Yeah, that's a smooth edge requirement. Right. Yeah, so, but before I talk about that, this is kind of roughly our attempt to draw a picture of the state. So you have this Moret unit cell. That's the big thing over here. And you have, roughly a few thousand carbon atoms inside. And at the scale of the carbon atoms, what is drawn over here is the spontaneous current that is generated. The scale of this current is in microamps, essentially, half a microamp. That's the kind of the scale. But the current pattern is changing on a 3 sublattice period. Okay, so if you like, this is, you have a U1 phase which you can move around. And if you get it into registry with your lattice, there's an extremely weak pinning of that U1 phase, okay, because of the mismatch in scales. You really think of it as a continuous parameter. But if you bring it into coincidence with the atomic lattice, this is kind of one caricature of the state. it goes between, it has plaquettes that have 0 magnetization and a magnetization plus and minus that gives you this 3 sublattice pattern. Okay, so if this was a state where the uniform magnetization of this kind of currents involved, you'd be able to detect it quite easily. But of course, the fact that it's staggered on the scale, it's going to be hard to directly detect it with some, with a squid or something like that. Yeah, another aspect of this is that although it seems to be just breaking threefold lattice translation symmetry, you would not expect a Goldstone mode over there, but essentially that threefold, that Z3 symmetry is enlarged to a U1 symmetry because of the mismatch in scales between the lattice and the Moiré scale. So you should see Goldstone modes, maybe with a very tiny gap, but should essentially see Goldstone modes. And then this question, this nice comment about edge states. Indeed, because the time reversal involves both the rotation of the Valley phase and regular time reversal, if you have a very rough edge, you would not get gapless edge modes. And so the simplest way of detecting the state, which would have been transport at the edge, requires certain special properties of the edge. Okay, so it's an open question. Maybe I'll return to that. Is how do you detect if this is really what is going on? Is there a direct way to detect this order parameter? And it's not very, yeah. Yes, yeah. So there is a coupling between the charge and the cube, the square of this order parameter. But again, those effects are, you can look at how it depends on the angle, and it's some very high power of the angle. So by symmetry, that's allowed. You'll have a coupling between, the Fourier component of your chemical potential and the order parameter squared. But the coefficient is going to be theta to some high power, I think 6 or something like that. So that coupling is extremely weak. Yeah, so there's, in this particular configuration, you can't see it. In other configurations, you can also get a net magnetic moment. Again, that's an extremely weak, even higher power, I think, of the angle. So that is going to be a challenging aspect over here. And, if there's really a density difference like this, it would lock into the lattice, and all of those locking terms are very weak. Yeah, I think the main effect of this order is really on the dispersion of the electrons. They get a gap. The electrons see this order parameter, and that is the sort of the dominant effect. And maybe there's a way to tease that out. You do STM on the electrons. You do scattering of electrons of defects or something. Maybe you can look for a hint of this order parameter in that way, rather than directly trying to probe it. Okay, so I don't have too much to say about superconductivity, but there's one interesting, maybe it's a coincidence, but it's a very lucky coincidence for this particular state. So, for example, in the spinless model, if you think of it as spin polarized electrons, if you were to get superconductivity, you would be getting spin triplet superconductivity. And we know spin triplet superconductivity is notoriously fragile, and if you have impurities, it'll be destroyed. But people see fairly robust superconductivity in these systems. So if indeed it is spin triplet, how do you explain that that robustness? And what can help over here is the fact that the time reversal, this state has a Kramer's time reversal. Okay, so if you go back and ask why superconductors are stable in the presence of impurities, there's a famous argument due to Phil Anderson, who said, although you think about pairing K and minus K states, if you literally paired K and minus K states, if you had impurities, K is no longer a good quantum number. Okay, but in fact, what you should be pairing is the Kramer's conjugate states, which are present even in the absence of having momentum conservation. Okay, so we have Kramer's time reversal symmetry. Your superconductivity will be robust, at least S wave, the regular kind of superconductivity, will be robust to addition of small number of impurities. You don't really care, just change the eigenstates. Okay, so of course here we don't have Kramer's time reversal in the sense of spin, which is what you have in usual solids. But you do have this Kramer's time reversal in the presence of this KIVC coming from this combined symmetry. Okay, so again, you expect the same kind of protection that if you have small angle scattering that doesn't scatter you between the valleys, the Cooper pairs, even though they are spin triplet, which coexist with this kind of order. You expect this order doesn't go away as soon as you dope it and get a superconductor. It would inherit the same kind of robustness. And we are also thinking about how interactions could lead to superconductivity, the same interactions that lead to the state, similar to how people discuss superconductivity in super exchange systems like cuprates. The interaction that gives you antiferromagnetic order, the J, also ends up giving you superconductivity. That's at least the belief. And also phonons may be important, and that's not sort of not exclusive. Okay, so now let me briefly talk about reintroducing the spin. Things get really complicated when you have spin. You have these 4 states. All of the symmetries we talked about, this U2 symmetry gets enlarged to U4. But you can identify a low energy manifold of states. And let me just mention it because there's one physically important thing that happens. So there's a large manifold of low energy states. It involves at special points, this is the charge neutrality setting. Special points in this degenerate manifold correspond to the spin singlet and the spin triplet order. Okay, so they're both there in this thing, and all kinds of weird combinations are also there within that manifold. If you have, this degeneracy of this manifold is broken by very weak couplings, the Hund's coupling essentially. And depending on the sign of the Hund's coupling, you end up getting, for example, if you have the usual ferromagnetic Hunds, you would get the so-called spin triplet state, which has this unusual property that you can think of it as 2 IVCs, 2 of these Kramer's IVCs for the up and down spin, but they're shifted by exactly half a period. Okay, because they're shifted by half a period, the net currents will cancel out. Okay, so you already had a hard time trying to figure out how someone could detect these currents that vary on the lattice scale. But in fact, if you had ferromagnetic Hunds, it turns out that the up and down spins, the actual currents also cancel out. And what you're left with is oscillating spin current. Okay, so it's possible that this order is even more hidden than what you would expect from the spin polarized model. Yeah, and you can also run this whole argument at plus and minus 2, where again people see insulators, and there's a different manifold for this degenerate manifold in the case of spin. Okay, so maybe I won't go into this, it's getting a bit too detailed. Let me just conclude this part, and maybe I'll spend 1 or 2 minutes on the surface topological order at the very end. Okay, so just to conclude all of these discussion on this twisted bilayer graphene, what I wanted to point out is these low energy nearly flat bands have some very interesting topology and geometry, which is we think is very important to understanding the nature of the interacting physics. And a key question, of course, is to understand what is the nature of these insulating phases, the superconductor, and I think it really goes back to this question of how you get the insulating state in different electronic systems. Okay, we are all used to one kind of electronic system like oxides or something like that, where typically goes along with antiferromagnetic correlations. But this may be a situation because of the non-trivial topology of these bands that ferromagnetism of some kind, some generalized kind of ferromagnetism is preferred, in which case it would completely change the story for what kind of superconductors appear in the vicinity of this system. Yeah, and finally, I talked about this Kramer's IVC. It's a very subtle symmetry breaking state. It has non-trivial band topology, and which could be important for what happens when you dope this system. And there are many questions about how it relates to experiment. If this is really the ground state, how does it square with all the different experiments that people are, have already done on this material? Okay, so maybe I'll take a quick questions on this part before I have just one slide about the what would have been this entire talk, but maybe I can just pause here for a second before I completely change the topic for 2 minutes. Yeah.
Make an understanding of the successive superconducting insulating phases, which are separated the superconducting phases being separated by the insulating phases? And
yeah, that's a good question. So first we can ask, how are the successive insulators related to one another? So somehow in our theory, it really gives you the insulators at even filling. That's where all these things conspire to give you a unique state. So the filling 0, which is the charge neutrality point, and plus minus 2. So our picture, roughly speaking, is both 0 and 2 have the same state, this KIVC. In the 0, you can think of it as a spin singlet version, if you like. You have up and down spins. It's not exactly what happens, but roughly speaking, up and down spins do the independent thing. And when you are at nuclear 2, you spin polarized. You forget about one set of spins, and you do the other set of spins is doing this Kramer's IVC. So then when going from one to the other, you should get a ferromagnetic transition, of the spin.
Right.
And maybe Erez will talk about things like that in his talk. At a much higher scale, maybe you get this sort of polarization of the flavors. So in between, we would say that, let's say you start in this Kramer's IVC state, and you dope it with some electrons. And that is the superconductor. You have some conducting state because you're off this nice commensuration for electrons and Moire lattice sites. You would expect to get a conducting state. Question is, what is that? Is it a metal? Is it a superconductor? And so on. And so that, there are different limits you can think about that. One limit is to start with a Fermi gas and then put in the same interactions that gave you this Kramer's IVC. Maybe in minus order parameter squared. It's a little bit like what you do in the super exchange kind of treatment of the spin fluctuations treatment of hoop rates. Think of a Fermi gas, very high, overdoping, small bit of antiferromagnetism, what kind of superconductor you get. That's one picture. Or you could think of something more exotic, that when you dope the charge, maybe the charge carriers are not just electrons, maybe they're more complicated and so on. Right. So you can't do neutron scattering on this, at least. Yeah, I'm even embarrassed to ask someone because the currents involved are small and it's a single layer of graphene. And it's the electrons that are within, the fraction of electrons taking part in this is basically the angle squared. So it's, yeah, you can't do it in neutrons. Maybe you can do it with the NMR or something, I don't know. There's some, but you'd also have to make sure you don't get averaging because of the breaking of the thing. So simple, having a large loop trying to pick up this current it'll get averaged out. You need something at the atomic scale, but which is very sensitive to these currents.
What is the expectation about the metallic phases, particularly when the band dispersion is small in presence of the interaction?
Yeah, that's a good question. So the band, when you fill these bands partially, that itself gives it some dispersion. So it's not like a fixed band and some interactions. The interaction is actually stronger than the bandwidth. So as you change the filling, your picture of what the band looks like completely changes. And so there are STM studies that look at the evolution of this in some detail, and I think Erez will also talk about that. It's pretty complicated. Metallic states are pretty complicated, I would say. So this, you'd expect this order will continue to some strength of doping, right? So you have this ordered state, and you have electrons and that you occupy in this other band. But very soon, if that density exceeds some critical density, you would lose the order, presumably. Does that happen before you get to the next lobe? Or yeah, those are interesting questions. Some of that is answered by quantum oscillations. You can look at the size of the Fermi pocket, and at least in some of these quantum oscillation studies, you see that density of electrons is really the deviation from the insulating state. It's like the order is preserved, and on top of that, you put electrons. Sometimes it's not. Sometimes it resets to the other value. So yeah, it's we will hear more. I think it's.
Yeah, so I have a question concerning the introduction of spin that you discussed briefly at the end. What I didn't get is whether actually the question was what kind of spin texture properties you will have on top of a KIVC, or whether you have to go look at competition between previous different states.
Okay, so actually the ground state you get is again a KIVC, but it has a big residual symmetry. And the symmetry actually, so let's say you start with a simple spin singlet state. It turns out the residual symmetry acting on the state, it remains a KIVC, but the spin texture changes. It has exactly the same energy, up to these Hund's terms that are very small. So you get a whole manifold, you can move around a whole manifold of this. So any point in this manifold is a KIVC, but its spin state is different. Yeah, so that may be important if you're thinking about spin textures. That is the low energy manifold of the spin texture. Okay, so let me just flash one slide, which was what I would have talked about otherwise if I hadn't run over here. So this is, I would have talked a little bit about this model in 3 dimensions. So this is a model, one of these exactly soluble models. It's kind of like the toric code, but there's an important difference. So just like in the toric code, you have, or rather like in a gauge theory, you have Ising spins that live on the links, but a pair of Ising spins, sigma and tau. And you can write down a Hamiltonian, some commuting projector Hamiltonian. The exact form of this Hamiltonian is not very important. There's a systematic way of writing down this Hamiltonian. And the nice feature of this model is that it's a model that has no bulk topological order. So you take this model on 3-dimensional volume with periodic boundary conditions. It has a unique ground state. Okay, but if you expose the surfaces of this model, it turns out to have a topological order, a 2-dimensional topological order just on the surface. Yeah, and the form of this topological order, that's this, it's called the 3-fermion state, very much like the toric code, except all the excitations, the electric particle, the magnetic particle, their bound state, all 3 of them are fermions. Okay, so it turns out this particular topological order is realized on the surface, and it's impossible to get that in 2 dimensions with time reversal symmetry. It's a model that has time reversal symmetry. Everything is real, but it allows you to realize this anomalous state. Something that's not allowed in 2 dimensions is allowed on the surface of 3-dimensional topological phases. So it's like the bulk is sort of like a topological insulator, like the Z2 topological insulator. And the surface is a completion of that surface state, which is gapped. It's got it's like a toric code. It's fully gapped, does not break any of the symmetries, but the price you pay is that you have this exotic topological order. You have excitations that are deconfined but only live on the surface. Okay, so that's this concept of surface topological order, something that might happen even in electronic systems with sufficiently strong interactions of the right kind. Okay, so it's a very interesting topic, and actually there are some connections to this twisted bilayer graphene. Some of the symmetries that we are assuming for the twisted bilayer graphene turn out to make that, if you assume all the symmetries are implemented locally, it turns out to be similar to the surfaces of some of these topological phases. In reality, those symmetries are not quite local. That's the way in which it can actually be realized. Okay, so maybe I'll conclude my lectures over here. Thanks again to the organizers and all of you who've stuck through this very long set of lectures and all the great questions. Thanks a lot.
Sir, I have a question regarding this surface topological order. I mean, this topological order will depend on the genus of the system, right? But how will you differ that topology from the bulk to surface?
So if you had no surface, right? If you took the analog of a torus but in 3 dimensions, so you identify the opposites surfaces, so there's no exposed surface at all. Now you have a purely bulk system. And you can, this is like a 3 torus. And if you had 3-dimensional topological order, you would expect to get some ground state degeneracy on this 3 torus. And you don't. You can show the ground state of this model is unique if you put it on a 3 torus. So certainly there is no 3-dimensional topological order. So now when you expose the surfaces, you can ask, is there some two-dimensional topological order that could be created by cutting out these surfaces? And that you can explicitly show. You can create excitations that live on the surface, and they are the same excitations as in this 3-fermion model. They have non-trivial mutual statistics. They have some self-statistics. They are like fermions, and they have all the right properties to identify with this 3-fermion topological order. You can explicitly compute everything because they're exactly soluble. Oh, you literally want to see the ground state degeneracy on the surface? That may be tricky because there is it's not an isolated two-dimensional system. It lives on this bulk. Yeah, that's a good question. Yeah, I'm pretty sure you'll see that if you can make a donut, right? And I'm pretty sure you'll get the right topological order on that donut. But it is true that the two loops are different. There's a loop that goes around inside the filled donut, and there's one that goes on the outside. But I think for ground state degeneracy, that does not matter. It matters for some other things, not for ground state degeneracy.
Something related to this weak topological insulator definition, which is
No.
yeah.
No. So this is something that could happen for a strong topological insulator. So take the Z2 topological insulator in 3 dimensions. It has a Dirac cone surface state, right? Bismuth selenide or something like that. It's got a Dirac cone on the surface. And we're told that you cannot get such a surface state, such a 2-dimensional state in a purely 2-dimensional system. That's the anomaly. And usually we are told that if you want to gap that Dirac fermion out, you have to break some symmetry. Either you've got to break the time reversal by putting on some magnetic impurities or magnetic atoms, or you bring a proximate superconductor. But this is a way out of that. You can get a fractional quantum Hall state on the surface, essentially, something like that, which preserves all symmetries. Yeah. So then you get the 2 layers next to each other, and you get a doubled model. You get 2 copies of the 3-fermion topological order. And that 2 copies is okay. It's not anomalous. It can be realized in 2 dimensions. It's the single copy that's anomalous with time reversal symmetry. Yeah. So when you put them together, it's just like saying you have a Dirac cone on top and bottom. You bring it together, then you get a pair of Dirac cones like graphene. It's all normal. It's fine. But it's the single one, the isolated one, that's anomalous.
What is the nature of excitations in the bulk of this, your model? When you go into the bulk, you have trivial excitations.
Yeah, you have trivial excitations. So it looks like you can make some loop excitations, like in all of these gauge theories, you have these loop excitations and point excitations. It looks like you can make these things, but it turns out they cannot propagate.
Like fractons.
This is completely confined. So the bulk is confined. Yeah. You can think of it as a model of loops, but the loops are mutual statistics. And it turns out the bulk wave function is completely related to the topological order on the edge. It's like you take the space-time dynamics of the edge, 2 space dimensions and a time. You think of the time as another space dimension, and the partition function of that model of that dynamics is really the wave function in the bulk. So there's a bulk edge correspondence, and that's how you write down this model actually.
So there are no propagating excitations in the bulk also.
Yeah, or they are all like
Toric.
Yeah, non-fractionalized, just some spin flip, integer everything excitations with all short range interactions, no mutual statistics.
Yeah. Yeah, I'm a little bit confused about this KIVC state in a Bilayer graphene. So you seem to say there's a 3 sublattice structure, so kind of like a transitional symmetry breaking. But this symmetry breaking is realized in the carbon atom level.
Right.
It's not at the Marie level. It's at the macroscopic level.
Yeah.
I see.
Yeah. So if you like the way we model this problem, we don't actually have the carbon atoms, right? You have like continuum Dirac model, but you have 2 valleys.
Right.
And the valley conservation is another U1 symmetry, valley U1, and that is spontaneously broken in this state. Now, if you track that back, why do you have a valley symmetry? Valley symmetry is really there because you can make translations at the atomic scale. When you translate at the atomic scale, the two valleys, they pick up different phase factors. That's like the U1 rotation. So when you spontaneously lose that, you lose the translation symmetry at the atomic scale.
So that means at the Murray scale, there's no, I mean, it's
Yeah.
symmetric.
Every Moire puddle looks the same. Yeah.
I see.
Right.